Okay, hello again. This is Ali, and I'm going to talk about model planning and feature engineering in data science. So let's first talk about model planning a little bit. Uh, the If you remember, the next step after doing the discovery and data preparation is actually to perform model planning. So there are some key activities that you need to do in this stage of the data science lifecycle. You need to ask yourself some questions. For example, if you have a specific problem, you need to ask yourself, how do people actually solve this problem by themselves? Are there a set of algorithms that can be used to solve this problem? How close my model and my problem is actually to those established scenarios? So when you ask yourself this question, then you can think of different machine learning models that are applicable to your solution. And then you could go from there and think about what are the assumptions that you need to make in order to use a specific machine learning problem. What are the parameters? Can you make a better machine learning problem? Is there something that people have not used but is applicable to your model? So those are some of the questions that you could ask yourselves. Sometimes the machine learning models are actually designed in a way that require a specific type of data. And for example, some machine learning models require, for example, time series data require data that is recorded as at a specific interval. There are some others that require you to give them a vector. Some of them expect a matrix as well. Some machine learning models could expect an image as the input. So you need to make sure that your machine learning model is actually accepting your input, and if not, make sure that you transform your data in a way that it can be accepted, or choose another appropriate machine learning model. So one of the first questions that you need to ask yourself is that what is your problem and how do you want to solve it? So basically, we went through this again when we talked about data science lifecycle. There are groups of and categories of techniques that you could use, and there are some example models that are within that category, and each of them are suitable for a group of problems. So for example, if you have a group of items that you want to kind of create a cluster of or group them by similarity, you could use the clustering type of algorithms. One example of that is k-means clustering. If you have some unlabeled data and you just want to know how many groups are there, or you're looking for finding some similarity between them, then again, you can use clustering. If you have a data set and you want to find a relationship between different items, for example, in online shopping, if you want to know whether people bought this product, and if they bought that, what else did they bought beside that, then that's kind of called market basket analysis. And then you're looking to find the relationships between similar items in which the people actually bought it, like using a data set. So you could use association rules group of algorithms, and a priori is one algorithm that we will talk about. If you have some input variables and you want to expect a numeric continuous output, then you can use linear regression and also logistic regression in a way that you may have some classes at the output, then logistic regression could help you with that. So these regression groups of models, they assume some linearity among your feature variables, and also you need to make sure that like your data is prepared to be given to these models. And they're very simple models, they're very powerful. If you want to find a relationship between those features, it's very important for you to know what's happening inside your model, and then how you could maybe adjust the output a little bit using the like inputs. Then you could use regression. If you have some text data, in general, you just want to analyze it. How many words are there? What are the topics? Maybe sentiment analysis, all that. You could use like text analysis techniques such as TF, IDF, like regular expressions, bag of words, and recently like neural networks like BERT are quite popular. One of the general areas of basically machine learning is classification. So in classification, you want to assign some known labels to some objects. So you have a picture of a cat and a dog and a bird, and you have these labeled images, and you give it to your model, and you expect your model to predict that an unseen photo of a cat is actually a photo of a cat. So you just take an image and then show it to your model, and you expect your model to know what kind of animal is in there. So if you want to assign known labels to objects like images or any other like input feature, then you're looking for classification. And we talked about KNN before, so we went through the whole algorithm. That's a kind of a lazy learning algorithm, which just looks for the k nearest samples. And there's also decision trees. Neural networks are also popular in this area. If you have some temporal data, like data that is recorded as a specific interval and deals with time, then time series analysis could be for you. Examples that when we talk about is ARIMA, and autoregressive, like moving average, those techniques. And finally, if you want to identify like a little bit more advanced like objects, and you want to identify patterns and use like some advanced technology that could imitate human brain, kind of. You could use some of the recent deep learning networks. So these networks proven to be quite useful and in applied science, in identifying face, images, objects, etc. in videos and cameras. They can be trained to respond to you as a like bot, and they can be trained to do many things. And the reason they're powerful is that they have multiple layers of neural networks, and each layer could learn a certain representation of your objects. And then all these different layers, when trained on a lot of input samples, they are able to predict results with high accuracy. But in general, they're at the end of the day, they're just mapping algorithms that they map input to output. They may not be necessarily be able to have intuition and to analyze and understand and think like a human being. So that's another group of algorithms. So convolutional neural networks, just deep neural networks in general, and long short-term memory LSTM neural networks are some of these. LSTMs are used for maybe more like a series data, time series data, and CNN is used for images. So you may ask yourself that so what is the difference between classification and clustering, because these are two main kind of groups of algorithms, and people sometimes confuse them. So there is the difference between classification and clustering, like both of them are trying to find some groups or classes, right? But there's a big difference between them. Imagine if you want to classify the objects in this photo, and also you may want to try clustering as well. So I started with clustering. So in clustering, you have no label data, or you may have that, but you choose not to use it. So basically in clustering, what you do is that you're given your data, and then your algorithm tries to find similar objects in this data using distance measure, like Euclidean distance or any distance measure that applies to your data set. So for example, your model could look at this, like in clustering, it could start looking at these different objects and says, well, it seems like these objects they kind of have the same size. These three actually have the same size, and these two have the same size. So it then tries to maybe it tries to create different groups and says, well, it seems like these two are one group. These are another group. And then finally, these two are one group. So, and it creates these clusters of like samples based on a specific feature. If it didn't have, so this is based on size, but if it didn't have the size information, and then like it had only color, or like based on color, if you want to kind of just look at these and try to classify them based on color, depending on what feature you have in your data set, then the clustering algorithm goes and says, well, it seems like these two belong to the same group. Like these kind of reddish, to some extent, this one as well may belong to another group. And like maybe these two belong to another group. And it could be a combination of all. Like it could look at different features, color, size, etc., and then tries to identify these different things. But it doesn't know how to identify them, because we haven't given any known labels and asked them to say, well, this is a yellow car, that is a sport car, or anything like that. On the other hand, in classification algorithm, you actually have some known labels and expect your machine to assign some of these cars or your objects to a specific class. So, for example, when you start learning this, when you provide these examples to your machine, what you do is that you say that, well, these are these, and this one is actually maybe a sports car. Okay. And there are some, or I don't know, racing car. Let me put it as racing. Okay, because they have been used in racing or for any reason. So what you provide might be different from what a clustering algorithm might obviously see at the beginning. Also, you might kind of say that, well, this car and maybe, I don't know, like this car, it seems like they have some engines in the back. Some of these cars are actually a sports car. And then maybe this group of maybe smaller cars or some other cars, they're just like regular consumer cars. So you need to specify all the examples, and then you say that, well, this is this is that. And then it's the responsibility of your machine learning algorithm to try to find some features or some way to identify these in the way that you like and you specified them. It might not be obvious for a machine at the first, because, well, the machine asks itself, how can I learn from, like, how can I put these two different cars, maybe with different colors, in the same group? Maybe it learns to do that by size. Maybe it looks at, I don't know, different features at the back. So it could use anything, but it usually, in classification, you have a specific task, you have a specific classes, and you want these data, your data to be actually put into that specific class. But in clustering, it's different. So uh, to summarize, in clustering you have unsupervised, or like it's an unsupervised learning, and you have unlabeled data. So by unsupervised, it means we mean that you do not have any supervision, or like you don't have any labels for your data. It's just some raw data that you have. And the output of the clustering algorithm is the clusters with their centroids. So for example, here a clustering algorithm could have created like 4 different clusters, and there are some centroids maybe around here, and you could see maybe a smaller cars could be close to each other as well. So it could be different things, different ways that you could model your data. We'll talk about k-means in general, and you'll learn more about that. So the difference now between them is that in classification you have supervision, and you provide label data to your model, and this label data could be something like, well, these are consumer cars, these are sports cars, and these are learning cars, and then you expect the model to give you the class or label of a specific object, an unseen object. An example of that would be the k-nearest neighbor. So this is the these are the main two differences between clustering, which is usually an unsupervised machine learning algorithm, and classification, which is usually a supervised classification algorithm. So so in general, we have different types of learning. So one type of learning is the supervised learning, which we provide the label data to the algorithm. The unsupervised learning is another type of learning that we do not have, or we do not provide label data, and we'd expect the machine to learn some underlying similarities or differences between the samples. And the semi-supervised data is actually where you have some labeled data, but most of your data is not labeled. So you use that labeled data to kind of start like creating your model, and then use the unlabeled data to enhance your model in general. Sometimes you start with the unlabeled data, you create some predefined parameters for your model, for neural network, for example, and then you pre-train your model using the unlabeled data, and then you start training it using the labeled data. And we have reinforcement learning. So in reinforcement learning, it's a different kind of learning in which you put your model as an agent in an environment, and in that environment, your model learns from the actions and the consequences of its actions, and then it repeats and repeats that experience until it learns how to deal with the environment. We use reinforcement learning in driving cars, in like agents that play video games. Like if an AI is going to play a video game, it just tries and tries and tries by trial and error to learn how to play that, and that's kind of a reinforcement learning environment. So so let's see how supervised learning actually works. In supervised learning, you have a labeled data set of size n, which you can show by using this set of different objects. So these are a set of samples, xi, which is a kind of a vector or a matrix, and then y of I, which is the label of that specific sample. So so this is how we actually show that. Show a specific data set which is labeled. And we call xi the feature vector of a specific sample, and it contains the different features that we have, and the number of features, which is usually unique for all the samples. Like it's better if you have the same number of features per sample, and we kind of call that total number of features D, or the number of dimensions of the sample. So if you want to show a specific feature, like for example the height or width of a specific object, then we show a of j at the top and say, well, that's the first one, this is the second feature, this is the third one of a specific one sample. And the data set is the collection of all of them. The y of I is actually represents the true label, the actual label of the data set, not what you are predicting. And it's in a pair, pair with the actual input. In unsupervised learning, we don't have any labeled data, or we are not using it. So we only have the xi's, and again, xi is the feature vector of the same size, and we call that x of I is a feature of a sample. So typical scenarios for unsupervised learning is actually clustering, dimensionality reduction, anomaly detection. Like if you want to know in anomaly detection, for example, if you want to detect a fraud and you have a lot of user logs, and you just take a look at the log of a specific user that is different from other ones. That's anomaly detection. In dimensionality reduction, you try to reduce the number of features, and it can be done using some algorithms like PCA, LDA, etc. So just to clarify something, the supervised learning, like in supervised learning, the goal is to predict the label from the input data. So what we want to build is that we want to build a system that receives the x of I, any sample. So this is basically it's a sample, and you give it to your machine learning model. So machine learning model, and you expect the this is what you expect. You expect the y of I, but that's not going to give you sometimes like all the times y of I. So this is going to learn to give you an estimate of y of I, and then if it is close to the actual y of I that you have, then it's gonna be like a good machine learning model. If it's not equal to that, so it's not predicting that label correctly. So your goal is to create this machine that predicts the true label of the similar to the sample data set of that specific sample. So so now that we know how these learnings work and we're preparing to choose a machine learning model, you need to think about preparing your features. So preparing your features and raw data, like your samples, anything, requires you to take some pre-processing steps, or sometimes converting or transforming your features. This whole process of identify meaningful, effective features for your model is called feature engineering in general. So there are some topics here that we quickly talk about. So as we mentioned, a sample is represented by that feature vector. So this representation idea is important because you can have different representation of an object. For example, someone could describe a cube by its height and width. Another person could take a photo of it. Another person could put it on a scale. Someone could give you the perimeter of it, so or area. So there are different representations of an object, and sometimes those different representations makes a huge difference for the machine learning model to try to learn how to identify new objects. So the feature vector is actually your representation of your sample. and like feature engineering in general deals with creating an effective or meaningful representation of a sample. So this effective representation means that you will be able to have some efficient machine learning. Sometimes there are ways to represent an object which is not wrong, but the machine learning does not learn very well from it. So it's very difficult for a machine learning model to predict the size of an object, like to understand whether it's a cube or a rectangle, or yeah, maybe a kind of if there's some spheres there or there's a ball, different things there. Sometimes it's difficult for it to distinguish between them if you just provide a black and white photo of a very bad angle, or you just provide the diameter of it. Like you just provide a diameter and expect it to know what it is. So if your representation is actually quite meaningful, then your machine learns better. In general, the deep learning, like in deep learning neural network society, the whole idea is how deep learning learns different representations and different features of an object. So by providing different layers, it is sometimes able to create its own features out of the data, and each layer presents that kind of representation. And sometimes it's not just about efficient machine learning for the machines, like some representation that works for the machine. It's also important that your representation is meaningful. And this meaningfulness is mostly for humans, so that the features are understandable by human. When someone is going to diagnose or use your machine learning model, it's important for them to be able to interpret the results and the features and understand what it means actually for these for your machine to predict a specific target. These two, like effective and meaningful representation, are not necessarily like it's a trade-off, but they're not mutually exclusive as well. You could have a meaningful, efficient representation sometimes for your machine, but it's not that easy to have both of them at the same time. Sometimes when you make it more efficient for machine, then it's less understandable for the human being, and vice versa. So here you can see an example of a data set, so that have different features. So here a data set looks like this. So this is something that you prefer for model from your base data, and from your raw data you get it, and then you need to transform it to create these features. So here you can see that we have kind of two features. One is the age and another is the height of, we can guess it's probably of a person. So age is from 10 to 20, and height we have from 100 to 160. And there is an adult here, and this is kind of looks like a label, and this is our, it could be our y of I if you are going to predict that. So these two, they're not adults, but these two are adults. And for us, it seems obvious that, well, if they're 20 years old over the age of, I don't know, 18, then they could be adults. But we may have as well have this trivial data, and we'll see that sometimes even these trivial data sets are not easy for a machine to learn. So this representation here is which is a set of all the samples, looks like this. So this is the same data here. So what you have is your x of i's, which is a vector. So the first sample is 10 and 100. So 10 years old, 100 centimeters, and this is the y of I. So basically I could say that the first sample for the, so let me just put it here. So this part here, it's x of 0, okay? And this one here is the first feature. Is the first feature. I could put it here of the first sample, and this one is the second feature of the first sample, and we just start with zeros. And this one is y of y0, it's just y0, and so on. So we start from actually I is from 1, so yeah, I could just change those to 1. Yeah. So it's x of 1, like the first and the second feature. And these are, each of these are actually one feature. So that's one feature that we have. And then it's the same for the other one. So this, we have in general 2 features, which is number of features per sample, and we have n equals to 4. We've got 4 samples here in this data set. So you could easily, like, this representation can be done easily in Python. Like, you could just create your data using this. You could put this in a list if you want. And it's a list of tuples. So these tuples of 2 items, one is a list of your features, another one is your output. You could also use this as a, you see, if you take a look at this, it's just simply a table. It's an array of 4, it's a 4 by 4 array, right? And you could simply put it in a matrix and just give it to NumPy and just start processing it by NumPy. Okay. So so when you start dealing with data, you will see that not all features are alike. There are some differences and you may need to deal with them differently. So in general, in statistics, there are 2 big groups of like levels of measurements, you could call them. So these are the level of measurements. So we have some qualitative, like features and like kind of data and values, and we have some quantitative level of measurement. So qualitative talks about the quality, it's not about some numbers. And when we have qualitative like types of measurements, we're mostly talking about categorical data. There are 2 main categorical data, two main types that you have. There are some, they're called nominal and ordinal. So in nominal, you have some name categories. Nominal is the weakest level of measurements that we have. So what it means is that we have some colors, for example, that are red, blue, yellow. And we just measure them and put them in a variable, in a feature, right? For example, x of, x of I number, I don't know, 1, this one could represent the color. So it could be a feature. And this could be any of these 3 values or other values. The problem is that in these named categories, it's very hard to find a relationship between these 2 different values. So is red and blue, blue is bigger than red? What is the number of blue? What is the number of red? So I know we could have RGB values or things like, and that representation is preferred actually to just these categories. So we may have some categorical data which could have some order, and we call them ordinal data. So these are categories like, I don't know, ordered categories like high school, What is the next category here? University. And like maybe when someone finishes the high school and university, they continue go to graduate school. And before that, you may have some other categories like, for example, like middle school. So these categories, there's something different from them that are just those colors. There could be a relationship between them. Like, you know that a university education is usually higher than a high school education. Like graduate level education, like a master's degree, is higher than undergrad level. So middle school, like preschool, kindergarten, those are all lower than the high school. So you can see that there are some levels here and they are ordered. So if you fill a form and fill a survey, and you choose these different categories there, then you may see that some people could assign numbers to them because they could be ordered. But those numbers are not really, you cannot deduct university from high school and say, well, the difference between university and high school is 2, while the difference between high school and middle school is 15. You cannot assign any numbers to them. They only have orders. So these are the nominal or ordinal qualitative categorical data that we have. But there are some other levels of measurements that we may have, and those levels are under the quantitative category. So in quantitative data, our data is usually continuous, but there are, again, 2 levels. One level is when you have some measurement that interval is actually important for it, and distance is meaningful in this category. So when you have an interval, for example, in temperature in Celsius or Fahrenheit, there is like the absolute 0 doesn't mean much in them. Like, it means, like, for example, we define absolute 0 in centigrade, the degree in which like water freezes, right? But we all know that like the absolute 0 is negative 273 Celsius, which is the 0 of Kelvin. So when we talk about degrees in Celsius or Fahrenheit, we do not have an absolute 0 that we could compare things with. We have another 0, or intervals are important. You could say that, well, it's 10 degrees warmer than yesterday, or it's 20 degrees colder than yesterday. You could actually assign something, but these are really relative, and distance is meaningful, but we do not have an absolute 0. So these are the interval measurements that we have. The most powerful kind of like qualitative data, the continuous qualitative data, the quantitative data, is the ratio data. So the ratio data has all the features of these, having a distance that is meaningful, numbers are ordered, but there is an absolute 0 there. So this absolute 0 enables us to create ratios between different objects. For example, the height, age, money, these are all ratio values. So we have a height of 0, but we don't have a negative height, right? Or we have an age of 0, and which is when someone is not born, or something is brand new. And regarding money, of course we have negative balances, but it's still considered like a ratio, because you can, so 0 means something, so absolute 0 exists, and 10 is twice $5. If you have $10, you could create a ratio and say, well, $10 is twice as much as $5. But in temperature, you cannot really say that, well, 20 degrees is twice as much as 10 degrees. The ratio does not have any meaning. Like you could say, well, it's twice as cold. So twice as cold for like from 20, or if you have 1 degrees Celsius and then 20 degrees Celsius, is it 20 times warmer? Not necessarily, but you could say that about money. So these are different categories of data, and we need to make sure we understand what features we have. And based on those features, we have to work on our data. So if you want to convert the qualitative data, like we have some categories, to quantitative data, then what can we do? Because machines usually don't understand just text. They could, and they can, but it's very difficult for them to understand that. So we want to convert these categorical data and features to some numbers so that the machines understand. So let's try to do something here. Think about it. How would you assign numbers to categorical data? So what are different ways? Like if I want to assign some numbers to these three like categories that I have, which numbers could I assign to them, and what are the consequences? Think about it. Pause the video. Think about it for a second, and let me know when you're done. And you could comment below or just send me a message of what you think about this. Okay. Okay. So one way to actually assign numbers, one trivial way, is to say, well, let's assign number 1. Let's start from 1 and to red, 2 to blue, and 3 to yellow. So now if someone filled their favorite color in an online form, and someone said, okay, what is your favorite color? And then they had a drop down, and then it had kind of red, blue, yellow, green, whatever. Then so you could, when you actually record that data in your data set and you have a column of color, then the values inside that could be, I don't know, 1, 1, 3, 2, 1, 1, 3, 2, 2. So you could have like when you assign these values to your categories, then you record those values instead of numbers. It saves a lot of space, by the way, and it could be easier for a machine to understand that. But what could be the problem? So if your machine learns this, and then when it tries to, like, it compares all this, for example, all these samples with these different numbers belong to one category, and this one to another category or class that you identified, then your machine may learn that on average the color of this group is what is a little bit less than 2, I don't know, 1.7. And in this group, the average is, 2.2. But what does that mean? What does 2.2 mean in a color, in a categorical data? Does average mean something? No. Like average for this is nominal data. We can't calculate averages on colors. So 2.2 means a little blue yellowish kind of thing, or 1.7 means like a red, which is bluish, mostly bluish, or blue that is a little bit reddish, you know? So what if we want to have red that is kind of yellowish, you know, like a combination of the, so it's probably a red. That means 2 is a red, and which is a kind of yellowish red, you know. Because if the average of, imagine one of the classes, like it calculates and learns that, imagine your machine sees people that have chosen 1, another group chosen 3. And it learns that, well, by average and average, that group of people like blue. Because the number 2 is the average of all these people. And, well, and 3 of them chose yellow, 3 of them chose 1. But none of them actually have chosen blue. And the machine concludes that, well, on average, they like blue. So it is not a good idea at all to use numbers for nominal data, which does not have any order. So be quite careful about that. So another example of that is when you have some role, like employee is 1, manager is 2, and intern is 3, and the machine learns that. And then what does 2.5 mean in that? Like a manager that is also an intern, you know? So don't use these. Be careful, but I'll tell you what to use instead. So what we want to do is that we want to use something called one-hot coding. I'll just talk about that. Just remember that converting nominal features to numbers will confuse your model. But if you have some ordinal data, it could be a little bit better. Some of the ordinal data could be converted. For example, if you have, like, if on a survey you have like different emotions like happy, neutral, and sad, you could see that this is an ordinal data that could be converted to a number, so it could be fine. But some other categories of ordinal data may or may not work, like infant, toddler, child, like these are different groups. 4.5 could have a meaning here, which means someone is between being a teenager and young adult, but it's not that accurate. It's not quite accurate as well. So be careful. It's not as bad in ordinal data, which is very well categorized and has some number values assigned to it. But for nominal data, I don't recommend using it by default. That's why now, instead of providing maybe these values, they ask you on surveys, well, from sad to happy, give us a number, like from 0 to 10, how happy you are or how sad you are. Then they could compare these values. So, so again, for nominal features, we have to prepare them somehow. So again, how do you think we could prepare that? So I talked about one-hot encoding. You may have heard about it, but what do you think that is? What do you think? How do you think we could assign numbers to nominal data in a way that doesn't confuse the machine learning models? Let me know about it. Write something in the comment below, or again, send me a message. Think about it for a second. Can you assign numerical value to nominal features in a way that doesn't confuse the model? Okay, let me give you an example. So if we could kind of separate each feature and each category in a way that the categories do not collide with each other, and they are all considered kind of different features, then we could make sure that there is no confusion for the machine. So if you have kind of red here and blue and then yellow, what we could do is that we could say, well, red is a different feature, blue is another feature, and yellow is another feature. And if we had red in a red category, we put a 1 here, and we put 0 in that maybe red feature. We say we have red, and then we create another feature called blue that the value of it is 1 for blue and it's 0 for other ones. And then we can have another variable or feature. We call this like features. We could have 3 different features for these, and we only set the feature when that specific category exists. So this kind of feature is called one-hot encoding. So in a way that if you look at this for red, we kind of put zeros everywhere and 1 just at one spot. And most of the times, at all times, usually there is only 1 category flagged and the other numbers are 0. So this is if we can have multiple colors or multiple classes. In one-hot encoding, if there are 2 colors selected, if the users select 2 favorite colors, you are able to just select maybe red and blue as well, which is also, again, fine. Depends on the machine. And zeros and ones, computers love them. So it's a very fast, machine-readable kind of categorization. It will increase the size of your feature vector, but usually it is worth it. So one-hot encoding. So in one-hot encoding, we transform categorical kind of features into binary features. And now this is an example of how we transform the colors, which is the nominal data, to one-hot encoding. So this is, again, quite useful, and this is very practical and very effective way that enables your machine learning model to learn better. You may need more examples, provide more examples to a machine, because as the dimensionality increases, your need for input data increases as well. But in general, this is one good way. So we talked about, just want to put it here. Yeah. So we talked about the transforming nominal data to, or like qualitative data to quantitative data. But what if we have continuous data, and for some reason, for example, from a statistical reason, or from for the type of the algorithm that we're using, we want to convert that into some categories, then what can we do? So binning is the answer to that question. So if you have continuous numerical data, and then you want to convert that to categorical data, why do you want to do that? There are many reasons. You will see an example and it makes sense to you. Then you could use binning. For example, age is a continuous feature. Like you have, it's a number. So basically it could be, age could be 0.1, 10, 15, 20, 100. But it's hard to sometimes expect a machine to give you an accurate age for prediction. So what we can do, we can represent age in some intervals rather than a continuous number. And it could be used for reporting or like changing the learning process using another algorithm. Let me give you an example here. So here we have some like we have some data. It's a table of data here, and this is the raw age that we have. Let's start from here. This is the raw age that we have, and it could be like different ages, like 0.2, 2.5, 4.9, like people that are close to V5, different data. And here we try to create some different intervals for this age. For example, we have age of, we want to create a bin called baby for age 0 to 12 months, toddler for ages 1 to 3 years, and so on. So these are the categories or bins that we create that represents different numbers. For example, let's find out the category that, I don't know, maybe 49 could fall into. So we want to put 49 in a category and 101 in another category called older adults, and this one is elderly. So let's take a look at the last category here, and we may find out that if you start from 45 and go to, I don't know, maybe 65 or 60, doesn't matter, and then everyone from 60 to, I don't know, to whatever would be considered an elderly. So you could just convert your data easily to these categories, and then once you create these different categories, you could start converting them into different bins. So you'll see how many categories you have. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 categories. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 values here. There are 2 ways of one-hot encoding. Like, one way is that you use the same number of variables, then you could select 2 or 3 of them. Another one is that you select one, like you choose, if you have like n categories, and so if for C categories, if C is the number of categories, for example, C here is 9, then the number of features that you choose could be 8. So the one way is that you just choose the same number, which is 9. So this is what we have here. Another one is choosing 8. We'll talk about that in linear regression in a way that some people say, well, if you consider all zeros for one category, then you could have one hot encoding for the other ones. But yeah, like that's another way of thinking things. Anyways, so we've got 9 categories, and we have 9 features here. So for toddler, we could start saying that, well, I put this one as 1, and then put 0, 0, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for preschooler, I put everything 0, and then I put 1 here. 2, 3, 4, 5, 6, 1, okay. Yeah, I guess I need one more. Yeah. So, and so on until the last one, the elderly, has 1 at the end, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros before that. Yeah, you see this completed here. So this is the kind of this is binning, how binning works, and you can see that different ages, like 22 falls into, will be getting this value, 4.9 will be getting this value, and 5, although so close, will get something different because it falls into another category. Sometimes using the raw edge could work. Sometimes you may want to use this instead. If you want to have different bins, and these bins could work for maybe some reporting purposes mostly as well. Okay, so let's talk a little bit about normalization. So sometimes when you have your numeric features, you want to make sure that your data falls between a specified range. The reason for this is that your model will be learning faster in this way, and sometimes it's actually necessary for your range, the ranges of the data to fall between a specific range. So this process of transforming the range of features to another range, usually 0 to 1 or -1 to 1, is called normalization. The formula for normalization is, like, you could change this to some extent, but this is min-max scaling. So the min-max scaling works like you get the difference between the maximum number for that specific feature. So this is a specific feature that we have here. You do this for all your features. So for a specific feature, feature J, you find the maximum number of that feature and subtract the minimum number from it. So it gives you the range, the whole range of the numbers in that feature. And then you calculate how far that specific feature is from the bottom of that, the lowest point, and then it gives you a range between 0 and 1. For example, if I've got heights, like in my data set, I've got different heights. I've got, I don't know, 10, 11, so on till 20. So if this is my maximum for the height and this is my minimum, okay. So difference here, the value for maximum minus minimum, this will be 10, okay. And the minimum will be 10. And then the features will be converted based on this formula. So this one will be 10 minus 10 over 10, which is 0. This one will be 11 minus 10 over 10, which is 0.1. And 20 will be 20 minus 10 over 10, which is 1. So you can see that the normalized value is now falls between 0 and 1. And this will actually make things quite faster for your machine learning model. And I will show some examples that it's actually changes a lot of things as well. So let me give you an example. Okay. Just give me a second. Okay. Okay. So, yeah, I just want to bring. Okay, okay, it worked. Just want to bring that back. I want to make sure that we're still recording fine. Okay. Yeah. Okay, so here, this is a data set that we have, and this data set is basically, it's the same data set we talked about. We showed how we have that. So we've got age of some people. Sorry, I mentioned height, so it could be height or age. In previous slide, yeah, I just meant height, age, sorry. Okay, so height, maybe in another language, maybe like the, I don't know, another format or scaling that could work, but yeah, I meant age. So if the age of a like user is like between 10 and 20. And so this is the data that is not normalized. And then we're looking to ask this machine learning one very simple question. We want to ask, okay, what is the what is the label for the specific person? So if I'm giving you this record, this feature vector, if I tell you that it's someone that is 20 years old and 140 centimeters, they're quite short for their age anyways, then they're an adult, because of course their age is over 18 or 19, and that's considered an adult. If someone with the same age is a little bit taller, 20 centimeters taller, they're still an adult. But for some other reason, these people here that are 10 to 12 years old, they're not an adult. So this is the raw feature that I have, and I am going to give it to an algorithm like KNN, or sometimes K-means if you want to do clustering, but here KNN. So K-nearest neighbor works in this way that it finds the closest sample, and like 1 or 2 or 3. Here assume that it's just, we want to find the closest sample in the database, and using that information we're going to choose what is the label for the other database. So so the question is, if we are going to have, if you are going to give this sample to our machine learning model, and it is going to find the distance between all these different kind of samples, is it going to choose another person which is 20 centimeter taller than that person with the same age, or is it going to find a person who is 12 years old and is 15 centimeter shorter than that person? So our data set, like the label data says this, but we're looking for this person, for this kind of data. But anyways, let's see what happens here and how the machine learning is going to compare that in an unnormalized data set. So this is the distance, like the Euclidean distance that is used usually for these algorithms. You could have another distance between your data. So this is the square root of the sum of squares of the differences between these two samples. So let's calculate that for the difference between number 3 and number 4. So let me move this around. Yeah, I could move that out of the way a little bit. So, so the distance between 3 and 4, okay, is calculated using the square root of distance between each of them. So Q1, P1, so it doesn't matter. I start with 4. So so for this feature, it's 0. Oopsie. Okay. So it's 0 squared because the difference between 20 and 20 is 0. For this one, it's 20 squared plus 20 squared. And this is going to give us 400, which the square root of 400 is 20. So the distance between 3 and 4 is 20. So now let's calculate the distance between 3 and 2. Okay. So the distance between 3 and 2, so we've got 8 difference here, so 8 to the power of 2, 64 plus, so 140 minus 125 is 15, and 15 15 to the power of 15 is 225. So so the total is 289, which the square root of 289 is 17. Okay. So now take a look at this. So the distance between these two is 20, and the distance between these two is 70, which is actually lower. So when we're using this raw feature, the distance between the person who is 20 years old and 140 centimeters, regarding being an adult or any other thing, the distance between them is actually less than a person with the same age, but with a little bit of height difference. Why is that? Like, if you actually compare it by their height, so this guy is like this person here is 15 centimeters taller than that one, but 20 centimeters kind of shorter than the other one. So if you compare that difference, it's just the difference is 25% of height difference between those two. But when you look at this difference, like, there is no difference between age, but this guy is 8 years older, which is like, I don't know, like 40, yeah, it's 40%. That guy is 40% older than the other guys, which is a huge amount. But because our data is not normalized, what happens is that the differences in centimeter is compared with differences in years, which is not fair, I guess. And this is happening because the data is not normalized. So if I go and take a look at this normalized data, and so this is what we had, and this is the Euclidean distance. Let me put this here. So this is the Euclidean distance that we calculated between each of the rows. Yeah, let me just remove myself. So the Euclidean distance between these different samples are actually shown here. So the difference between 3 and 4 is 20, and between 2 and 3 is 17. And yeah, the difference between the distance between fourth sample and the third sample is actually larger than that. So what happens if we try to normalize the data? So if we normalize the data using the min-max scaler, the data would look like this. So yeah, the 20 years old, like for this feature, 20 is just considered 1, and then 10 years of age is considered 0. So now when you compare this normalized data, you will see that the difference between our sample and the second sample is 0.8, but the distance between the third one and the fourth one is only 0.3, which is what we would have expected. Like, if height is not the only thing that we were looking at the age as well, then this is what we're looking for. So the difference between the third and the fourth one is actually should be lower than the distance between the second and the third one, which is now a huge difference. And all this happened because of normalization. And even look at this table. This table is even shorter than, like, literally smaller than that, because the numbers are smaller. All numbers are smaller. It's faster for your machine to work with these numbers. You will need less memory, depending on the data. Like, it's floating point operation, of course, but there are some pros and cons. So using raw features, like the second sample is the closest sample to the third one. Using normalized features, the same features, we just normalize the data. the third one will be assigned, the fourth one will be the closest one to the third one, using, like, I don't know, k-NN or k-means, all these algorithms. So yeah, if your data is not normalized, then yeah, 12 years old like person could be considered an adult. There is also another way of doing things, and that is another way of pre-processing your data, and that is standardization. So there is a small, not very small, but there's a difference between normalization and a standardization. In a standardization, we rescale the feature values so that the whole data set has the properties of a standard normal distribution. So we want our data to look like a normal distribution with mu of 0 and sigma of 1. So this kind of, most of the data will fall between kind of 0 and 2, something like that. But it will work better if you have a lot of outliers. So outliers will ruin your normalization, because in normalization, if you have a very big maximum and minimum value, then what happens is that, let me just give you that example. Okay, so in normalization, imagine your maximum, like for height, for example. Now, let me give you something for income. So that's the example they provided. Imagine that you want to normalize the data for income, and your maximum income is, I don't know, the CEO of a very large company, and the maximum is $2 billion, and then the minimum is 0, of course. Okay, and then most of the data that you've collected is maybe from average people with regular income or student income. Then your data usually could look like this, because you've got some people with a few people with very high income, okay, and then most of the people range in the medium income. So if you use min max scalar normalization, okay, then this is going to be 1 and this is going to be 0 using normalization. But what happens is that most of your data will fall between, I don't know, maybe 10%, like between 0 and 0.1, which is it's not a great way of representing things for your machine. You want to expand this. What you want to do, you want to expand this into something like this, so that this could be, I don't know, 0, this could be 1, 1, and this could be around 2. So you have some data which is some outliers which could be around, I don't know, 2, 2.5, or 3, and then most of your data falls between -1 and 1. So this is a better representation, which is done using a standardization. And then using normalization for cases that have a lot of outliers. So a standardization is better for you, for your data set or for a feature, if you have a lot of outliers. Also, in unsupervised learning, again, like k-means, standardization is preferred to normalization, because it makes all the variables like quite comparable, which is very important. You want all your variables to be comparable to each other, because it's like a voting system. You want to see how close the samples are, so you want all the averages or like movements, everything, you want it to be similar. So yeah, the difference in the formula is that instead of the minimum, you subtract the mean of your distribution of all the samples of a specific feature and divide it by the sigma. So yeah, the standard deviation of your data set. So it will give you the standard, kind of a standard distribution for your feature. So another thing you want to do on your features is you want to handle missing values. I talked about that in my demo, but in general, what you can do is if you have any missing values in your feature, sometimes if your database is so huge and you don't have a lot of missing values, you could just simply remove that example. If there's just one example, yeah, you could just remove that. And another thing is what you could do is you can use learning algorithms that could deal with missing data. For example, naive Bayes is one algorithm that could deal with a lot of parameters and with missing data. You have to see what you have there, and you have to compare different values, different models, if I'm not wrong. So imputation techniques can be used for dealing with missing values. So in dealing with missing values, sometimes you can replace them if you're allowed to. If you want to, you should consider the consequences of replacing missing values, because if you replace the missing values with something that is not that has another meaning, then you're going to have incorrect data, biased data, like fake data, which is going to have unpredicted outcomes for your model. But some techniques, some imputation techniques, is replacing that missing value with the average value, which is the mean or the mode of the feature. You could use the previous value. If your data is ordered, you may use previous value using forward filling, or next, like the previous value using backward filling. These are some of the, this is using the next value. So if you have 1, 2, 3, and 2 is missing, then 1, nothing, I don't know, and then you have 3. So by adding the average, you put 2 in there. By previous value forward filling, you put 1 in there. By using the next value for back filling, you put 3 in there. You could, by adding a 0, you put 0, a specific number, you could just put 5, anything you like. Sometimes interpolation, you could just use interpolation as well, and using the previous or next few values. Interpolation here gives you 2, because it just finds out that, well, it's 1 something 3, what is the missing value? It's 2. It uses maybe another machine learning algorithm. And you could use regression algorithm, which is, again, you should look at the interpolation algorithms. Most of them are just linear regression anyways, to predict those missing values. So there are sometimes, you could sometimes learn, create a machine learning algorithm and give it the X as the other features and give the Y as the missing feature. For example, if this was one of your features and then you had another feature which was, I don't know, let me tell you, 2, 4, 6. This is a very trivial example. So if you have this here, and first of all, it's not a great example because these are highly correlated. The correlation between them is just almost 1. If this is your X and you make these, so these are all your features, but you put X as your input, Okay, and you create a machine learning algorithm that could predict y. So and y is your missing feature. And then this is a way to deal with missing values. So the training sets, you train it with 2 gives 1, 6 gives 3. Okay, you train your machine learning algorithm by that, and then you ask, okay, what does 4 give us? And then it tells you, well, it seems like it is going to give you 2, which is your missing value. So this is another, like, you could just use interpolation, or you could simply use other techniques. But whatever you do, any machine learning like decision tree, anything you could use, it's your decision. Try to find try to first decide if you want to replace them using imputation, then try to impute them. All in all, when you're selecting a machine learning algorithm, you have to consider a lot of different scenarios. And so you need to consider the fact that whether you have categorical data or numerical features. Some of them are better with that. We'll talk about those different models that are good for one or another. The nonlinearity of the data. Is your data linear or nonlinear? Can be modeled. Do you think your model can be modeled using a linear data? Then you could use linear regression. If it is not linear, then you should choose another technique. Explainability, how important it is for your data and the results to be explained to non-technical people, because some models are explainable, some of them are not. Neural networks, most of the times they're not. Decision tree is a very good and explainable model. Linear regression is the same thing. You want to also consider training speed and prediction speed. Some models there's not, for example, KNN doesn't have any training, but prediction speed is very low compared to other machines. The reason is it just compares the data with all the data sets there. There's no parameter estimation in k-nearest neighbor. On the other hand, neural networks, the training could be very time consuming, but prediction speed could be quite faster than KNN for a very large data set. Memory consumption, how big is your data? Like for KNN, if your data cannot be fit into memory, then it's like reading the hard drive over and over multiple times just to find the output. But some models are, like some machine learning models are very hard to fit into the memory during the training, but they're fast when you want to actually maybe predict the model. And also number of features. How many features do you have? Do you have a lot of different features? Did you have one hot encoding? How many examples do you have? Do you have a lot of examples? Then you could consider deep neural networks. If not, then you want a simpler model that could work better for you, because if you use an airplane for something that is for just moving a small package in this city, like moving something too big for that, it's not that efficient. Deep neural networks, sometimes they're so big that they will just memorize your training data, which that's not what you want. You want to have a model that understands, that gets the general concept of that. We'll talk about overtraining and undertraining and overfitting in a while. Anyways, so we're going to talk more about this, and then we're going to talk about the different learning algorithms and how good or bad they could be for your example. If you had any questions, let me know. I use these, the machine learning book and also the data science book, and for some of the topics in this series. Okay, thank you.